He served as postdoc fellow in School of Life Sciences, Beijing School of Technology, Beijing, and School of Biotechnology, Jawaharlal Nehru University, New Delhi. He also served as an assistant professor at School of Basic and Applied Sciences, Department of Chemistry, Galgotia University, Greater Noida, UP. He did his MSc and PhD from Department of Chemistry, Jamia Millia Islamia, New Delhi. He has published 20 research papers in reputed journals, edited 2 books, filed 2 patents, and 15 book chapters. His area of research dedicated to nanobiotechnology, analytical chemistry, design and fabrication of nanostructure materials, nanocarriers for drug delivery, and polymer chemistry. Without further delay, I'm going to welcome Dr. Anujit Ghoshal. Welcome to you, sir.
Yeah.
Most welcome.
Yeah, thank you. Thank you for the kind introduction, Dr. Abhijit. Basically, Dr. Abhijit is a very good friend of mine, and we know each other for a long time, and we have survived the period of PhD together. So, yeah, we are pretty cozy together, and we have worked a lot and have learned a lot from each other. And I'm really thankful to the whole organizing committee, especially the Department of Biochemistry, Shivaji College, for inviting me for this particular lecture. And I hope all the listeners will learn something from today's presentation. And first of all, good morning to everyone. And really sorry that because of me, you guys have to wake up on Sunday morning, right? So although it's night here, but I know that it's morning over there. So let's start with this particular topic. Although I know that you guys, every one of you have heard about nanotechnology or nanoparticles somehow, because in today's world, this word nano, it is coined everywhere. So you cannot, not know this particular term. But to understand this is a bit difficult. I will not say it's very difficult, but to understand this, you have to read a bit more. So I will keep my presentation very basic, in which I will discuss about the nanotechnology, what is basically nanoscience, which many of you may have heard about. So it will be a brushing up. And after that, I will talk some basics about the synthesis process and what is the importance of nanoparticles and what are the things we should consider while we are working with nanoparticles. Then I will talk about the properties and then certain applications which are important and on which I have worked. So let's start. So this is the basic path which I have followed so far. So I have done my bachelor's in chemistry from Delhi University. Then I have done my master's and PhD from Jamia Millia Islamia. I worked as an assistant professor and then worked as a postdoc in Jawaharlal Nehru University, Beijing Institute of Technology, Dalhousie University, and right now I'm working at University of Manitoba, where my focus of work is on nanotechnology-based materials for in food industry. So I will definitely brush up about that also at the end. But let's first start about the basics. So what is nanoscience? We all know that nanoscience, we say it is a branch of science which specifically deals with the materials which are in nano range, mostly from 1 to 100 nanometers. So these are a few examples or transmission electron microscopic images of materials, of nanomaterials, of metallic nanoparticles, which shows different shapes and sizes. So if you can see that we can characterize a particular material, or we can say a material can be in 3 dimensions. We can always talk about a material in 3 dimensions. So at least one of the dimension if it is in nano range, we can say that particular material is a nanomaterial. Or let me simplify much further. So what is nano? Basically, nano is, it's not a very big thing, but nano is a scale. It is a measure, like we use rural normal scale to measure anything, right? In centimeter, in meter, in kilometer, right? So similarly, nano is a scale in which we measure the material in nano range. So anything which is in between 1 to 100 nanometer range, or anything where we will say something, say x multiplied by 10 to the minus 9, we will say that is a nanomaterial if we can characterize that particular material in that particular range. So basically, if we classify the nanomaterials in broad way, then we can say the nanomaterials can be of 4 basic categories. That is 0-dimensional nanomaterials, 1-dimensional nanomaterials, 2-dimensional nanomaterials, and 3-dimensional nanomaterials. So 0-dimensional nanomaterials are mostly spherical in nature. They are particulates, and or we can say metallic nuclei. They are like equal in all the directions, in x-axis and y-axis and z-axis. They are like similar or same. That's why we call them as 0-dimensional nanoparticles. 1-dimensional nanoparticles are, or nanomaterials are those in which at least one of the dimension will be in nano range. Say, if we are talking about this nano rod, then we know that the length can be long enough. It can be in micro range, that is 10 to the minus 6 meter range, but the diameter will be in nano range. It has to be, otherwise it cannot be considered as a nanomaterial. In 2-dimensional material, for example, a very common example is graphene or graphene oxide sheets, in which at least 2 of the dimensions will be in nano range, and mostly the height and breadth are in nano range, and the length can be in micrometers or in several hundred nanometers. In 3-dimensional materials, all the 3 dimensions should be in nano range and can be considered as 3-dimensional nanomaterials. So why is there a thrust on studying these nanomaterials? So if we see, or what brings our more interest on particular material is the change. So anything which changes, we are more interested in focusing on that particular change. So we always like to understand why such particular material is changing, what is happening. Because if we know, if we talk about the basic chemistry, so you all know that we generally characterize any particular material based upon its atomic number. So if you guys ask a simple question, if we are reducing the size of that particular material, are we changing the atomic number? No, we are not changing that anything. In atomic scale, we are not changing. We are just reducing the size of that particular material. And because of that change in size, certain properties or most of the properties are changing. Although the fundamental or the basic characteristic properties, that is the atomic number, atomic mass, and all those things which that are characteristic to particular material will not change. But due to change in the size, due to reduction in that particular radii of that limitation, that many properties are changes. Many properties becomes advantageous. Few of the properties does get deteriorated, but most of them are advantageous, and most of them we use them for our own application. So this particular ceramic, if we see, it is red, like it belongs to some ancient time. So at that particular time, they don't have that particular idea why. Or for example, nowadays we know about dyes, we know about different coloring media, some organic molecules we generally use, or we paint it simply. We can go to the market and buy a paint. But at that particular time, to give particular colors, people, or I will say the chemist or the scientist at that particular times, they are using metallic particles, or I will say metallic nanoparticles. They didn't characterized it as nanoparticles, but they were using that, and on that basis they produced different materials of different color based upon all these properties. Because anything, if is changing, size, texture, arrangement of the particles or the atomic structures, the properties changes. Why it changes, how it changes, I will definitely discuss in following sections. Secondly, why we are studying nanomaterials? Because of these properties which are changing, we are getting some value added functionalities in this particular materials, in any material which are generally converted into nano range. And because of that, they find their application in various industries. And because of their application in various industries, all these important applications, it's all about money. So, it gets more benefits to the employer, to the users. So that's why to understand the properties of these particular materials very important. For example, if we talk about pharmaceuticals, if we don't understand a particular material, then we cannot use it for ourselves, because it can be dangerous, it can be very toxic. And it is very well known that certain or some nanoparticles at particular concentration are toxic, which is, I think, for every material, or even for food. If you're eating food too much, then it will be toxic to us. So we have to manage, and that's why we have to know at what particular concentration, how much amount of that particular material will be toxic, and how much of that particular material will be beneficial to us. For example, if you talk about, say, our facial creams or sunscreens, mostly in most of the sunscreen, there are silver nanoparticles in them as a protective agent or as an antibacterial agent. But if we are using too much of that, then it is toxic to us. So we should know what is the limit, and because of all that reason, we have to understand that particular material, how it works, how it behaves, and how should we handle it for our own benefits. So as I already told, that this is another thing, that nanoparticles or nanomaterials of different metals, metal oxide, or carbon-based materials are finding application in various industries. And because of that reason, because of that only reason, we have to understand why we are studying nanomaterials or nanoparticles of a particular material. So because of the importance of carbon-based materials, see, I already told you about that classifications generally we do as 0-dimensional, 1-dimensional, 2-dimensional, and 3-dimensional nanomaterials. So another broad classification is inorganic nanomaterials, organic nanomaterials, and carbon nanoparticles. If you say, you can definitely say carbon nanomaterials or carbon is, and you can consider it an organic nanomaterials. But because of the various properties and various applications of carbon-based materials, we have separated this particular class, and we generally study this particular class of material for our own benefits, or to properly understand how these particular materials are behaving. Then if somebody asks, you are a nanotechnologist, or you are a nanoscientist, or you work in nanochemistry or nanophysics or nanobiology, biotechnology, you have heard all these words. What does all this word or all this area signifies? So this only signifies one particular or one important aspect, that nanotechnology or nanomaterial synthesis or nanoparticle applications involve different areas. It covers different objectives. And that's why this particular area is considered to be as an interdisciplinary area, where a person from physics background can also work, a person from biological background can also work, a person from chemistry or some mathematical department can also work. Nowadays, if you see, there are different areas or different companies, they're employing different peoples. Or say, if you talk about computers or electronics, they're employing chemists, they're employing physicists, they're employing biologists, and they're employing mathematicians or computational guys to devise a particular model and to understand or to find a particular application of such materials. So nanochemistry or nanotechnology has occupied a large area of science, and it is a multidisciplinary area to understand all the properties of these materials. So you should always try to think broad and not particular only for chemistry point of view or physics point of view. You have to always think broad in this particular area. So now, I hope everyone has understand. And if you guys have any doubt, definitely you guys can ask me in chat that if you have any questions which you don't understand. So I hope till now you do understand what is nanoparticles, or what is, if we talk about nano, so it is not a very big issue. Simply, nano means a range, and it is a way of classification of certain material at particular range, right? And because of that particular range where we are limiting it, that we are saying it should be only say 100 nanometer, it should be only 50 nanometer, or we are restricting it to say 10 nanometer, the properties, various properties changes. So now, if we talk about the synthesis of nanomaterial, so you have to understand that we cannot formulate any particular material without giving energy. So as we know that in today's world, if you go to any shop, we have to give some money. Similarly, in sciences, in chemistry, or in sciences, or in synthesis of any particular material, of any material, whether it is in nano range, or whether in micro range, or whether whatever particular organic molecule, we need to spend some energy on it. So now how we are spending the energy, or how we are utilizing the energy, that matters, or what particular route it is taking, that generally can broadly be classified as, top-down approach or bottom-up approach. You may have heard about this. So top-down approach means that we are starting from a bulk material, from normal, which we see from for our eyes. For example, we are starting from a mountain, and we want to generate a road in between, or we want to create a tunnel from within the mountain. So what we have to do, we have to break it, right? Similarly, so most of the top-down approaches involve this particular phenomena, where we start breaking a big chunk of a material and try to convert it into smaller range. And the final range at what we stop is in nano range. And this type of materials will be obviously called as nanomaterials or nanoparticles. And this particular approach, or the route followed, will be termed as top-down approach. So there are various examples in which, or techniques or processes which comes under top-down approach. So one of the most simplest is the ball milling. In ball milling, there are small circular metallic balls, and the materials comes in between it. And so whenever it comes in between it, it breaks by a chunk, a small piece. So similarly, when this particular process repeats number of times, the material will be converted into nanoparticles, or laser ablation method. So in this, generally we incident a high energy beam of energy to a particular material, and it gets converted into smaller particles or smaller chunks. Because of high energy, that particular material starts to break down into different forms, or it will be converted into vapors and then redeposit, right? And that will be deposited into some nanoforms. And all those approaches, all those methods will be classified under top-down approaches. Now, bottom-up approaches are very simple. Yes, top-down approaches are a bit expensive also, and more energy consuming, whereas bottom-up approach are more energy efficient and not that expensive compared to top-down approaches. And in bottom-up approach, the ability to control the size of the material is also higher, although that same can be achieved from top-down approach, but we have to be very specific about the parameters which we are following. So in bottom-up approach is just the opposite of the top-down approach, which starts from the atomic range. And I hope everybody knows the atomic range is in pico range, right? Picometer, that is 10 to the minus 15 meter. If we talk about the radius of a particular atom, right? So we start from that and we start building up. So one atom comes close to another atom, and another atom comes to this particular two atoms, and they form particular clusters. And then this cluster will result into materials in nano range. So in this approach, we start from the bottom and we try to mix up, or we try to do some science or do some chemistry through which these small atomic materials will come close to each other, form a cluster, and nanoparticles will be formed. So there are different processes which comes under this particular approach, the simplest is reduction methods, in which we generally use some base, or say NaOH or ammonium hydroxide, as a reagent, as a reducing agent, because when we are trying to use this atomic scale material, generally we start with ions, metallic ions. So metallic ions, we know that metals are, they always need electron, because they have a tendency to donate electron. So generally they are, for example, if we take say zinc chloride, so zinc will have always a 2+ positive charge. So what we will do, we will, because it is its nature that it will give the electrons. So if we put it in water, it will not take the electron back, because it is like a rich guy. And a rich guy, what does a rich guy do? He always flaunts. He will put his hand in the pocket and throw the money out, means if he has enough money, or he is not valuing the money that much. So these metallic ions or these metals are like that. They always try to give the electron. Anybody wants electron, they will give it. So in a particular aqueous environment, they will not take the electron back. So we have to create an environment where they will take the electrons, and they will form metallic cluster. They try to come close to each other and ultimately result into nanoparticles. So I will discuss a typical synthesis formulation, and then we will move forward. But while we are doing the synthesis, either from top-down approach or bottom-up approach, it is not very simple, because when we are synthesizing nanomaterials or nanoparticles, because of their small size, their reactivity is very high, their surface to charge ratio is very high. Means these particular terms you have always heard about it, but you have to understand this. When we are reducing the size, try to understand what happens. Like, you try to understand it like say an onion. We are opening different layers of onion. So what will happen? More and more surface will get exposed. When more and more surface get exposed, the more electrons, internal electrons, will be exposed. And because of all that reason, we know that in chemistry or physics, what happens? As I already gave an example, that in normal life, the exchange or whatever we do is done through money, currency. That's the currency. It's a give and take mechanism. Similarly, when we are talking about these nanomaterials, because of that opening of different surfaces, high surface area getting smaller, and more surface area is getting exposed. Because of that reason, there are so many electrons. And in science, or in these reactions, electron exchange is everything. If you actually think about it, if you just close your eyes and think about it, what is happening for any reaction, in any chemical reaction, mostly there is a give and take of electrons, or there is a sharing of electrons, right? So electrons is everything. So when the particle size of these materials are reducing, what's exactly happening? All the electrons are getting exposed on the surface, and because of that reason, they are highly reactive, and because of that reason, they have different properties. I will briefly discuss about this, how and what is changing and what is happening. But because of all that reason, what is happening? The synthesis becomes very difficult, because at a particular moment it will be formed. It's like, humans. Sometimes they are your friend, and sometimes they're your enemy, and sometimes they even don't know you, right? So similarly, these nanoparticles are formed, and then they're not there, because of the small particle size or high surface to charge energy or ratio or electrons. What happens? The nanoparticle is formed, and suddenly they will react with other nanoparticles, they will react with other nanoparticles, they will react with other nanoparticles, and again we will get a bulk material or in between material from nano or bulk material. So our objective was to synthesize nanomaterials, and we won't be able to get that because they are highly reactive. So we have to think about a way how, or we have to optimize particular criteria. We have to take care of all the parameters which are involved during the synthesis, the solvent, what we are using, the temperature, the time for which we want the reaction to move, and the time when we want the reaction to stop. That is very much important. Because if we don't control that, if we don't control the size, shape, and composition of these nanomaterials, then they are of no use. If, for example, you can think it like you have a car, say Porsche or Mercedes, right? But when you want to go somewhere, the car has its own mind. Sometimes it will say, okay, let's go. And sometimes it will stop at the middle of the road. So I hope in that place, you will be happy with a bicycle, or you will be happy with a bike. You won't go towards that Mercedes because it's unpredictable, because in the need of hour that will leave your side, it will not be of any utilization. So similarly, we are trying to find, or we are trying to synthesize some materials for our own benefit. And if we cannot control the properties of these materials, so they are of no use. We are spending so much energy, so much chemicals, so much efforts. But if the properties are not consistent, if the properties are not same what we are expecting, or if it is changing with time, as I was telling, nanoparticles are formed, it is giving you the properties, but we did not do anything to control the size or the shape or the composition. More and more clusters are forming, the property, it will lose its property, it will lose its advantages. And because of that reason, nobody will use that particular material. Then the stability of the material, and the last one is important, the scaling up of the method. Because generally in laboratories or in any particular place, we generally form small amount of nanomaterials. We try to characterize, we try to analyze the properties, and then we report it. That's how a publication works. That's how scientific community works. But generally, when we go to an industry, for example, we are making a facial cream, right? Say for becoming more and more white or more fair, right? So we are going there. So every time if we use, every new batch will not be same. There has to be some change. Okay, it cannot be same every time. It will change something. Or we don't want to put our efforts 100 times. We try to form one time, but the quantity will be equivalent to 100 times. And when we try to do that, generally the scaling up becomes very difficult. Reproducibility becomes very difficult because of unpredictability of these nanomaterials, because of their small size, because of their high energy, because of so many electrons involved. So we have to control all those parameters. That's why nanoscience, or we say synthesis of nanomaterials, becomes difficult. So till now, we did understand what is nanoscience, right? What is nanomaterials? So I hope it is not a big deal. Again, if you have any issues, if you don't understand this, definitely you guys can definitely ask me over here, over chat, or you guys can email me anytime. So this is a typical synthesis, mechanism which generally followed by any particular nanomaterial or any particular synthesis. So generally, it starts with the injection of the, metallic species or the reactants, which we want to react, which we want to do something for us. And once it reaches a particular point, when it starts forming, the process of nucleation starts. So nucleation is the first step which took place during the synthesis. Nucleation means, hopefully you guys have done, it's like a seeding. You have done a crystal formation of some potash alum. Generally, we make a concentrated saturated solution of salt, and then we put a small seed of particular geometry in the solution, and we let it be there for overnight. And what happens? The crystal grows, and it has different phases, different crystal structure, right? So if we don't put that particular small seed, what happens generally, if we come to the next stage, there is number of salts or number of crystals, such crystal structure at the bottom of that particular bottle or the beaker. So if the seeds are not there, so generally a chunk of material are formed. So seeding, or we will say the nucleation, is a very important process during the synthesis of nanomaterials. So generally nuclei are very small, very, very small, even smaller than the nano range materials are formed or precipitate out from the system. And after on those nuclei, generally the growth process starts. So in growth process, what happens? There is a small particle, and around that more deposition will take place. And because of more deposition, the size of those small nuclei will grow at a particular range. So that particular process we say growth from solution method. Afterwards, when they reach a particular concentration, the equilibrium process starts. And because of that equilibrium process, a particular phenomena of Oswald ripening takes place. In Oswald ripening, what happens? There are some small nuclei which are left, which did not get bigger because of that during the deposition process, and there are some big nuclei. So generally, it is a simple science that smaller particles have higher solubility as compared to the bigger particles. So what happens? These smaller particles, because now the equilibrium is changing, right? More and more salt has precipitated out from the solution, and they have been deposited on the nanoparticles. So the solution is deprived. Now the solution is not saturated. It can dissolve material. It can dissolve the metallic species. So the small particles generally get dissolved inside and will redeposit on this bigger particle. That particular process is known as Oswald ripening. And the last one is the saturation. So generally, we control all these processes. We control the timing. So what particular size we want, up to what particular range we want the reaction to go. So if you can see that, the nucleation, up to the nucleation process, generally a typical size range is, 0 to 10, 20 nanometers, or say 30 nanometers. And during the growth phase, the particle size increased from, 20 to say 200 nanometers. And during Oswald ripening process, generally the particle size, because the small nuclei are dissolving and they are forming bigger nuclei. That's what, thermodynamics will process, because it is a spontaneous process. It has to happen. So we have to stop it at what particular time we want it to be, at what particular range of particles we want. We have to stop it. And after this Oswald ripening, there comes the saturation part. At this particular level, what happens? That all these small particles or the big particles, what have happened, they will come close and they will form agglomerates. And we never want that, because once the agglomerates are formed at saturation state, the nanoparticle properties will definitely diminish, or the nanomaterials will go away, and they are of no use to us, because there is no specific particular size. So it is very important in nanochemistry or nanoscience that we try to synthesize material of particular size, of uniform homogeneous size, because if the size of the particles or the shape of the particle is not homogeneous, is not uniform, then the properties will be different. They will not follow a particular trend. And if they do not follow a particular trend, then they are of no benefit to us. Same, a particular material can be toxic, and a particular material in different form will be beneficial to us. So we have to understand and we have to control those parameters, and we cannot take it for granted. So this is an important point. Always remember, if you want to work in nanoscience, you have to control it, control the parameter. So this is a typical synthesis method which I used during my PhD for synthesis of nanomaterials of nickel and nickel oxide, and nickel with different shapes, different morphologies. So simply by changing the concentration, the initial concentration, and the centering temperature, the shape, size of the nanoparticles formed were different. So every process, I will discuss this particular process just in a while, but I'm just trying to make you understand this particular process, that, how much, what concentration of the nuclei or the reactants we added, that also, govern the shape, the structure, the formation of the material. Because if we see the temperature, although it's a big range, see 400, they are same, but at 400, one of them at 400 degree will give me a nanospheres, nanoparticles, and one of them at 400 degree will give me nanorods. So what actually happened here, that over here the nucleation rate was higher, okay, and over here what happened, the growth rate was higher at a particular direction. And what governed this particular phenomena is the molar concentration of the metallic ion, metallic species, which I added. So over here the metallic species is less, and over here the metallic species is high. Now again, another question, why? So all these things, whatever happened, we have to understand, we have to report, and we have to follow a particular, why this particular trend happened, that we have to understand always, right? So afterwards, if I take another molar concentration of metallic ions, what is happening? I'm getting cubes. So same material, same starting material at different particular concentrations. What I am getting? Different shapes, different sizes of nanomaterials, right? So what we used, this is a very simple, very facile method in which we use a castor oil, simple vegetable oil, which we have, which we generally use. And if we have any, say, coconut oil, say some other oil, we can use that also. So what happens, they are generally polyglycerides, or they have this particular, they have this, electronegative groups in it. And because of these electronegative groups, which are mostly oxygen in it, they have a tendency, because of this negative charge, and I already told the metallic species or metallic ions are generally, electron deficient, because they generally tends to give the electrons to the society. So we create an environment in which the metallic ions are there and electron rich species, these are electron deficient metallic ions, and these particular units or polar groups are electron rich. So they will start interacting with each other, and a particular moment will form, that there will be a precipitation, or there will be nucleation process will start because of this closeness, because of this particular conjunction. They will start forming, and we will get our nanomaterials. But as I previously told you guys, that we have to control the synthesis. So timing, at what time you stop the reaction, for how long you will heat the particular material, and what particular material you are using will define the stability of the material. Since we used castor oil, and these are mostly, carbon. So what happened, when we get the nanomaterials, we get a coating of this particular material on the top of it. So what ultimately we got the nanoparticles, but we got the capped nanoparticles. We had a coating, a secondary coating on the top of it. We did not do any additional step. That's why this particular synthesis method was important and better, because we are not doing any additional step, and we are capping our material using an organic layer, which will protect it from further growing up, from further increasing the size, or further getting oxidized when it comes into contact. Because of high reactivity, if we take nanomaterials in our hand, they will not tear for a long time. If we take it for say 10 minutes, I will say, there will be oxidation taking place, because nanomaterials are highly reactive, and they will convert from metallic state to oxide state, and oxide states are the stable state. So it's a spontaneous process, thermodynamical process, you cannot stop it. So through this synthesis method, after capping, if we cap it through some different, there are different methods in the literature, in the Google Scholar, you can search, there are different journals, you can find there are different capping agents, and those capping agents are used for that particular purpose only. So what is exactly happening? As I told you, the properties change, right? Why the properties change? First of all, I told you, whenever we are making the size of that particular material small, we are opening more and more surface. And because of that more and more opening of the surface, the energy, the electrons are getting exposed. And because of that, their reacting ability or interacting ability increases. And that's why all the properties are changing. Their magnetic properties changes, their optical properties changes, their conductivity changes, their melting point changes, their thermal property changes. So this is a typical example of the energy diagram of these such materials. So in bulk material, there is a continuation, but if we go to nanomaterials, there are discrete energy levels. And because of this discrete energy levels, they behave specifically. They behave differently from the bulk nanomaterials. So now, till now we have tried to understand a little bit about nanomaterials. What are they? Why are they behaving differently? What are the things which should keep in our mind? Why that particular synthesis process is happening? What should we take care of? What should we avoid? And what should we do, right? So now another basic question: what is nanotechnology? Okay, till now we understand what are nanomaterials, what is nanoscience, what it does, right? Now, what is nanotechnology? It's very simple. So nanotechnology is utilization of these nanomaterials for different applications, or formation or creation of functional materials, some devices, okay, through which we can exploit the properties of these materials for our own benefits. So if we are developing some technique or technology using these nanomaterials, we will talk that particular branch of science or that particular branch of chemistry or physics as, or biology as, nanotechnology, right? So I will discuss about nanotechnology, how we have, or many people have developed some surface protective coatings or applications through these nanomaterials, drug delivery applications, optical applications, how the change in magnetic properties is beneficial for certain particular applications, how they are important for catalytic applications, how they are important in food industry. And what is the big thing? We are not doing anything new, actually. We are just copying nature. We are trying to follow nature. We are trying to mimic nature, because nature has also many things. I will show you some examples. If we actually characterize them properly, they all are in nanorich. They all are in nanorich. And because of particular arrangements, we see those properties. If we talk about, say, butterfly, do you think they have all different colors? Actually, there is some particular dye in it. Think about it, or go and read about it. Lotus leaf, if you see, or in our culture, or we know that we always say that leaves or flowers are the purest form. We say they are never dirty. So it is not out of respect, actually. It is out of science. We know that they are clean. We know that they are pure. Just wash it in water. We don't have to wash them with soap, right? We are not washing them with some detergents. We are not doing that, right? We just max to max. We take the flowers, or we take some leaves from the tree, and we put some water on it, and it's clean. We say it's all clean. There's no issues, right? Then high definition lenses, right? We are in physics. If we talk about, we want, scopes or laser focused materials, or in our phone, there are so many high good digital lenses. We all are mimicking nature. Then spider web. Nowadays, we are creating some particular structures which are supposed to be very strong. Honeycomb structure, we say, like a honeybee creates its house, right? So honeycomb structure, because they are so strong, that particular arrangement, when the scientists are observing that, they are saying it is a better arrangement, it is a better stability that results into good properties. So all these colors, all these structures, if you closely analyze, then you can see that they are arranged in nano order. There are arrays. And because of those particular arrangement, we are getting those particular colors. If you talk about lenses, there's small circular. See, if we see these. So we are trying to mimic nature, and try to behave, or try to create some materials which can which can at least close to this natural material. Okay, and because of all these properties, if we can see that lotus leaf, as I told you guys, that we are trying to use, or we are trying to mimicking, or we are creating Asian paints. If you see, they are saying just shake the house and the house is clean. So what's actually happening, we are creating a material or surface, or creating a material will provide the surface which will be like lotus leaf. But what is actually happening, we know that lotus leaf have super hydrophobic structures or super hydrophobic surfaces, and because of that, any water drop will always create like this. They will not adhere, they will not there will be no adhesive nature of any material, and that's why it's always clean. So we are trying to create those nanostructures on the wall through paint, through using nanomaterials in paint, so that we will get a hydrophobic surface on the wall. And if rain or if wind blows or if anything happens, our wall or our houses will be clean. So if we talk about the optical properties, so I already told you what happens when the nanoparticles or nano range, any material comes in nano range. What happens? The electrons gets exposed. So based upon the size or the structure of the material which is formed, the number of electrons, the arrangement of the electrons, the arrangement of the band gap is different. And because of that reason, they will interact with the external light beam differently. And when they will behave differently, they will show different colors. We know, right, why a particular material show a color? Because it will absorb that color and it will excite, right? The electron will get excited, and the energy which it absorbs, the complementary color we generally see, right? So based upon the number of electrons, based upon the absorption, based upon the size, what happens? They will show always different colors to us, right? See, as I was telling you, see, this is the color. It is not the color. They don't have different colors on the wings. They have different arrangement. This is a scanning electron microscopic image of the wing of a butterfly. Few of the butterflies do have different colors, but not all of them. They have different arrangement, and when light falls in it, the electrons get excited in different way, and that's why we can see different colors, right? See, if you can see over here, this will further explain this optical property. If it is a one-dimensional material, then the arrangement of the energy bands will be different. That's why the coloring will be different. If it is in two-dimensional, right? If it is in two-dimensional, then the arrangement will be different and you will see different color. And if it is in three-dimensional arrangements, see on the top, on these, because of all these arrangements, you will always see different colors. Whenever the shape, size, and anything changes, generally, it's not always, but the change should be significant. It is not possible there is a small change and you will expect that there will be a big change in the color or there will be a big change in the property. It doesn't happen. There should be a significant change. For example, if you're changing from this, like a Icelandic, right, a triangle to a hexagon, what's happening? The color is getting deepening. When it forms an octagon or a mixture of triangle and these octagons, the color becomes blue, right? So there should be some significant change, and because of that, the properties will change. And now how this particular property of the nanomaterials are exploited or used for our own benefit. If you talk about smart windows, if you talk about monochromatic glasses, it is glasses, okay? It's a printing mistake, I will say. It should be glasses, right? Then there are aeroplane windows, Now they are trying to develop certain aeroplane windows where if there's too much sun, the color of the window will change to, it will go to dark so that you will not feel too much sunlight in your eyes. You don't have to close the shade. You can still enjoy the view without closing the window. So all these materials have are being employed in different aspects, right? So the second particular very important part is surface protective materials, or I will say the paint, the example which I was giving you, paint. So we know that corrosion is a spontaneous process, right? So we know that if there is a steel like this, however new we take the steel, but if we don't take care of it, what is take caring? Every time we cannot rub it, right? We cannot always put oil on it so that it will not get corroded. We have to make a barrier between this particular steel surface from the atmosphere, because the atmosphere has oxygen. So we generally produce some coatings which will give us a surface similar to lotus leaf, right? That has a high surface area. Sorry, that will have a high contact angle value and low wettability. Means you cannot wet that surface. Anything will get wet if it comes in contact to it. But if that surface property is like that it does not comes in contact with that particular material, then what happens? Definitely it will be always clean, and it is always providing a barrier to that particular material and to the atmospheric pressure. So it will reduce this rate of corrosion, right? So second thing, generally we are using organic dyes, right? Organic dyes are toxic, and they generally goes like whenever we are synthesizing, they are generally going to to water sources, and they are creating a lot of toxicity actually. So nowadays what people are doing, they are using metallic pigment. Different metals have different different colors on them, and because of those particular colors, the mixture of those pigments, this metallic pigments in nano range, will give us different coating materials, and they will be very strong against corrosion. How they will be strong, I will discuss with you. But first, a typical synthesis method. So generally, whenever we're synthesizing these coating materials, so we either follow a in situ synthesis, means the nanoparticles which we are talking about, they will be found within the material, or we will first synthesize the nanomaterials and then we will add those nanomaterials to the system. Whatever way is, they are generally composed of two separate units, subunits. One is organic and the another one is the inorganic, mostly metallic salts or metallic isopropoxide, which will go inside the material and form this interlinks. Because of this interlinks, we will form a inorganic material, organic material, inorganic material, organic material, a hybrid. We will create a hybrid or nanocomposite materials. All these nanocomposite materials will help us to stabilize that particular surface, protect that particular surface, create a good lustrous area exposures, and protect it from the corrosion, right? So this is a typical mechanism. This is a typical chemical skeletal of that particular material. So all these, CH2, these are the hydrocarbon chain or the polymeric unit which is there, and all these are the metallic nanoparticles which can be added externally or which can be synthesized within it. If we synthesize within, then they are known as in situ, and we can definitely add them from outside, then it will not be in situ, and they will form a complicated or complex or hybrid structure like this, which will protect the surface. So if you see, if you can consider this as a metallic surface, and this is a coating with nanomaterials, and this is a coating, same polymer coating without nanomaterials. So try to understand these are the corrosive ions, because it is a spontaneous process. If this particular atmosphere comes in contact with this particular metallic strip, it will start the corrosion process, because it is spontaneous. You cannot stop that particular steel plate or iron plate will convert into iron oxide. It will become red, right? We have seen all that. So to avoid that, we need this particular layer of the material. But if there are no inorganic materials, we know that inorganic materials have more strength, more mechanical stability, or more resistance to different corrosive ions, and they always create a hydrophobic surface. They try to create, because of these nanostructures only, they will create an hydrophobic surface that will not allow the water molecule or the environment to come in contact. And because of that only reason, our surface will be safe, right? Another property which changes when the particle size decreases. So far we have seen that if the particle size decreases, what happens? The electronic state changes, right? The number of electron changes. And because of all that, the optical property will change. Another thing which changes is the crystalline arrangement of the material. And because the change in arrangement of the materials, whether the material will result into a crystalline state or whether it will be amorphous, that will change. If the arrangement is systematic, we know that that is the basic definition of crystalline materials. And if the arrangement is not systematic, then it will be amorphous. Mostly, whenever we are converting the material in nano range, they comes as crystalline in nature. Because why crystalline? Because the arrangement of the nuclei is in very much order, right? And because of that reason, we will get generally what this is a technique which we use in nanochemistry or nanotechnology to identify the characteristic or identify a particular material, that whether that particular material is a metallic or metal oxide, or there is some coating or there is some change in arrangement. We can do it from X-ray diffraction patterns, right? So if you can see, if we have these strong spikes in particular material, these are characteristic to any particular material. For example, I have written it, this is nickel nanorods, or this is, if I hide this nanorod, we can simply say it is a nickel material in nano range because we have formed it, but this will be characteristic to this particular material. A nickel oxide will have different other peaks, but it will not have the same peak. So this will classify, this will differentiate between nickel oxide and nickel. Similarly, this will differentiate between nickel oxide and nickel. Okay, so similarly, if it is a different material, say barium titanate oxide, then there will be different peaks. The peaks will be of different order. They will have different HKL values, and that's how we will differentiate it. But amorphous material will be always like this. If there is a carbon coating on the surface, generally most of the materials become amorphous. So generally a strong peak comes, which is due to carbon, and we cannot see any particular peak. Okay. So another thing which changes is the magnetic property of that particular material. So we know about iron, right? Everybody knows iron is used in different places. So iron is generally ferromagnetic in nature, right? Ferromagnetic means when we put a particular magnet, it will attain all its domain will be in a particular direction. So it will have a ferromagnet, strong magnetism. But when the size of these materials are smaller, when the size becomes small in nano range, what happens? It do not have a specific direction. Okay, and when it do not have a specific direction, it will form a particular magnetism, that is super paramagnetism. So if it is in bulk, if it is in large size, then it will be always considered as ferromagnetic because they are large, they are aligned at a particular direction, their magnetic domains are at a particular direction, they are strong, they cannot be dispersed in water. Can you consider putting iron in water and you expect that particular material will be stable in water? It is not possible, right? We cannot think about it. We can cut the pieces of iron, any small pieces, and put it in water. We cannot get that particular material. We cannot disperse, we cannot dissolve that iron species in water. But when we synthesize it in a particular technique, so that each size of the particular nuclei becomes smaller, because of the change in the magnetism, what happens? They can be easily dispersed in water. And because of that reason, because of that very reason that it becomes dispersed in water, the application of this material change, and which is very beneficial to us. So, okay, I will discuss about the properties, how this magnetic materials are beneficial to us in later stage. So this is another important aspect of nanomaterials, adsorption ability. As I was talking, when the particle size decreases everywhere, whenever we are talking about nano, whenever we are talking about the properties of nanomaterials, always think like, what is happening? So what is happening? The size is decreasing, right? So when the size is decreasing, what is happening? More surface is getting exposed. And because of that, they have high adsorption ability, right? They can take more and more material into it, right? So because of that reason, we can use them as magnetic adsorbents, and we can clean our water or industrial waste where there are so many pollutants. We can even remove heavy metals using these magnetic materials, and we will not lost it. We will not lose this particular material to the environment. Why? Because they are magnetic in nature. If you put a magnet, see, for this particular example, that it is a methylene blue dye, which we generally use in any industry in dyeing process. So we add our nanoparticles, we shake it for, say, for a small time, and then what happened? Then we put a magnet, and within 2 to 6 minutes, what happens? All the nanoparticles went to the side, and we can definitely remove it. We can scoop it out, and our water becomes clean. So because of this particular ability, such materials are greatly employed for adsorption purpose. So this is the typical UV spectra of the material. So it is a combination of two dyes. One is methyl orange dye, and these two peaks are due to methylene blue dye. So when we are putting our nanoparticles in it, what's happening? It is adsorbing both of the dyes. Although it is adsorbing this methylene blue a bit higher and methyl orange a bit lower. So we can say they are specifically adsorbing what? Cationic dyes, okay, or anionic dyes. So it always depends what type of material we are formed, and based upon that, it will show typical properties. Now, as I was talking about magnetic materials, because of that change, that is ferromagnetic to super paramagnetic, which allowed that the metallic nanomaterials in the water, what happens? These materials are used in cancer therapy, that is typically termed as hyperthermia. So due to what we do, we change the external stimuli, we give it a stimuli, we change the alternating current, and because of change in the alternating current, these nanomaterials becomes heated, and when they get heated, and if they are in response, if they are in contact, and we know that there is a heat flow always, right? High temperature to low temperature, and when that happens, that particular cell, we know that our cell cannot survive very high temperature, and because of that, those cells will die. So if try to imagine, if we have a targeted WFD and those nanomaterials are close to cancer cell, and we heat the nanomaterials up to a range, what will happen? Simply, those cancer cells will die, right? So based upon that particular theory, hypothesis, what happens? They have developed this hyperthermia process in which they are using them for killing cancer cells. So definitely there are some drawbacks also, but today we are talking all about positive to understand, and to eradicate the drawbacks, we are generally processing, or we are trying to improve the technique further. Then we use these magnetic nanoparticles for drug delivery application. As I told, the high surface area led them to get attached with different drug molecules, and they can be delivered and they can be released at on demand. When we want, they will release that. Then there are MRI contrast agent, right? We know that to image our body, generally, initially, previously, what we used to do, we used to drink dyes. The patient had to drink a particular dye, which will give a particular color to all the organs inside our body, right? And these dyes are generally organic dyes. At particular concentration, they are okay, but they do have some side effects. Since iron is a mineral, right, which is which is okay for our body. Our body has it. So our body has a process or technique to mineralize it, okay, take it out of the system. Our body can do that. So these nano iron based contrast agents are marketed and they are used, and more research are going on to shift from these organic dyes to magnetic materials. So this is a typical example of hyperthermia. What happens? We change the current, and because of that reason, the particle nanomaterials will get heated, and because of that, it will either release the drug, or if it is in contact with that particular cell, it will kill them, right? Okay. Another important property is formation of typical structures. And these particular materials, polymeric materials, these nanostructured polymeric materials are termed as hydrogels. So it is a typical class of polymeric material which has, these are the scanning electron microscopic images, right? Which shows there is so much porous structure. It will be like a solid bulk, right? I will show you one example which we have synthesized in our lab previously. And because of these small pores, they have high volume ability to absorb high amount of water, more than its actual weight they can absorb. Okay, and these materials have enormous applications. They are used for burn victims. They are used for delivery of drugs, sustainable delivery of drugs, because once there because of these small holes, these spaces, we can load drug molecules within it. So this is a typical example how what happens. So all these spaces we can fill them with our drug molecules which we have, which we know, say organic molecules, right? And due to variation in the pH, what happens? They will release it slowly. So if we control the size, if we control the structure, we control the release mechanism. If we increase the temperature also, it will expand, and the drug will be released. So what I'm saying, these nanotechnology, this is nanotechnology, right? If we can pattern this, if we can form this in different way, so the properties will be different and they will have different applications. So this is a small video. I don't know whether I can play it or not. So I think I cannot. So this is a magnetic hydrogel basically. So if you can see it in the shade, so when it comes close to it, what will happen? It will, it will come close to the magnet. So similarly, we can, but when we actually view it, the structure will be like this, right? But in bulk, meaning by our naked eyes, we cannot see. We need some instruments to verify it. So this is another example of these nanocomposite materials or nanopolymeric hydrogels, so which has typical structure like this, the sheet-like structure. They're pretty stable and they are in liquid state. Okay, they are not in solid state. We convert them into solid state when required. So this is a typical example of say some clinical operation, and we know that this particular sector is bad, maybe say cancerous cell. So we generally do what? We cut it, but we cannot cut all the cells, right? But we took a big chunk of it, and then what we did, we filled it with our hydrogel material, which is in liquid state. And we know that our body has a particular temperature, and this is a temperature sensitive material. What will happen? It will be converted into solid gel. So two things will happen. First, it will fill this gap. Okay, if the gap is not filled, what happens? If in our body, if there is some cut, because of constant movement, we will get more hurt. So if it is filled by something which is not toxic to us, it will help us to recover fast. Because of this microstructure, the cells or the tissue can grow within, and because of this drug loading, what happens? We can control through external heat. We can kill even these leftover cells, right? And if the drug is loaded, generally doxorubicin is loaded, dox generally we say, because of this treatment, when we alternate the magnetic field, what happens? These drug molecules are also released, and our expected thing happened, that we cure cancer. This is how the research is proceeding, right? Yeah, I was talking about the imaging, right? So this is a typical imaging setup in which we are trying to observe what is happening with the rat's heart. Maybe this is the liver, maybe these are the kidneys, right? We can image them very particularly, very specifically with the help of quantum dots. And these are the magnetic resonance images in which we are using magnetic nanoparticles to image the the organs of a particular rat, to see the brain structure of particular rat. So what is happening because of a small change? What we did, we converted a bulk material into nano range. Because of that, its solubility increased, because of its magnetic property changes, because of its stability changes, and the properties we can exploit, right? So we always have to think about science in that way, what we can change, what we can achieve, right? Another important properties which is like growing on nowadays a lot, there's a very hot topic, that is nanocatalyst or nanometallic catalyst, nanozymes. We also term them as nanozymes. Definitely you guys have heard about enzymes. Enzymes are catalysts within our body, right? Which helps us to process all the daily activities within our body. We cannot see them. But due to different reasons or due to specificity of these enzymes, they're highly valued, they're highly expensive if you want to buy them from outside. So what people are doing, or what scientists are doing, or researchers are doing, they are trying to create metallic nanoparticles or metal oxide nanoparticles, which can mimic particular natural enzymatic activities. So if you see, so these are so many materials, so many magnetic particles, magnetic, metal oxide, okay, or mixture or composite materials, which can show different enzymatic properties. Although the problem right now is that the yield or the conversion process is small. So people are trying to work out and try to do some modification so that the efficiency can increase. So what is the application if it has some catalytic property? So we know that these drug molecules, we have so many organic molecules, organic chemists are very important. They can create so many hydrophobic materials which are highly potent, means they are like drug. They can kill bacteria, they can kill viruses, even for COVID, right? They have developed different molecules which can kill COVID. But what's the problem? These hydrophobic molecules are not soluble in water, and our body is mostly made up of water, and that is the transport system in our body. So if it is not soluble in water, if it is not dispersed in water, what will happen? We will put it in our body and it will precipitate. So the dose which should be distributed throughout the body, what will happen? It will be deposited at a particular point, and it should give us the beneficial property, but it will give us the reverse, or it will not do its work because it is not distributing. So generally what we do, we try to attach this active molecule or drug molecule to certain groups which are soluble in water, highly soluble in water. So what happens when we make them one? They become soluble, and we use these nanoparticles or nanomaterials to do a specific activity. What is that specific activity? To break this bond. Since this is a glycosidic linkage, we say this is glycosidase activity. So once it breaks the bond, what will happen? It will release the drug over there. And once the drug is released, we'll get the antibacterial activity, right? So this particular type of setup is known as prodrug. Means initially it is not drug molecule, but after a certain process, it will become a drug molecule. So this is another one. So yeah, these nanoparticles were synthesized by me for definitely the catalytic activity. We saw the catalytic activity. So this is the mechanism which happens. So we know what happens whenever there is some interaction. Say this is the metallic material which we, or any nanomaterial which we supposed to be acting as a catalyst, but it will only act as a catalyst when it has some interaction. So try to understand, if we don't talk to each other, we cannot make friends, but we cannot make enemy, we cannot do anything, right? So it will be like we are in vacuum, we are in a space where we cannot talk to each other. So they need to interact, and if they interact, they may show some properties. So what happens? They provide, so we know this is a catalytic process, right? If it is a catalytic process, it will provide an alternate path to reach the product, right? So it will not form the normal trend, it will give a alternate path, and because of that, the process will be done by that particular route. So once they start interacting, if they are not doing on its own, we generally use secondary stimuli. So either we can use H2O2, we can use hyperthermia. Hyperthermia means alternating the external magnetic field. Because of that, there will be heat generated, and because of that, the catalytic activity may occur. And what is the catalytic activity? Right now, we are talking about the glycosylation activity, means it will break this particular bond. This molecule will go away, and this molecule will go away, and we will get our desired product, right? That this particular molecule will indicate the reaction has happened. So this is the UV visible spectroscopy, which shows that with time, more and more product is converted, and because of that reason, more and more nitrophenol is generated, and the intensity of nitrophenol will increase. Okay, so now this is so far we have discussed about nanomaterials and why they're important, what particular property is changing, and all those properties, how they can be beneficial to us. So now let's talk about some food, right? Obviously today is Sunday, and you all guys are sitting in front of computer, maybe eating something. But what are you eating? Definitely something tasty. But the question is the taste everything? Because nowadays, because of the processing or making them, fast, microwaving it or heating it at different times, what we are doing, we are destroying the nutrition. We are creating an imbalance in nutrition. And because of that imbalance, so as per the CDC, Center for Disease Control and Prevention, what it says, that all the infants, right, many pregnant ladies, even the adults, are deficient in particular nutrition or minerals or vitamins. And all that high sugar, or we need taste, right? Being Indians, we generally eat a lot of sugar, a lot of salt, a lot of saturated fats. We all want fried food. So all this are causing a lot of nutritional imbalance and creating different diseases. So we cannot stop eating them, right? That will be impractical if I say, okay, stop eating that. It's not possible. But what we can do, being being smart enough, we can alter, or people are changing the nutritional delivery system, or the structure, food structure we are changing, so that we will eat the food, the taste will be same, but the nutritional content or the properties will be enhanced. So another big problem, what is the big problem? That we know that there are so many bioactive molecules, right? But their solubility is very less, right? We can create so many vaccines, but because of low solubility in water, we cannot, right? There is so much food shortage, nutritional imbalance, but we cannot do anything because of low solubility. Because if we extract, say, if we are separating the proteins, separating the minerals, separating the vitamins, which we can add separately, because we want people to eat, we want people to have those particular vitamins. We don't want them to eat vitamin pills. We don't want that. We want them to eat vitamins with food, right? Not as a medicine. We want them to eat protein, more protein, not in pills, right? Because there are so many pills. People can definitely take the pill and crush it on the food and eat. But that is not feasible. The taste will change, the color will change, the texture will change. We don't want that. So generally what we do, we formulate a particular system mostly. And what type of system? I hope you guys can guess now. Nanosystems, right? Nanostructured materials. We can take those drug molecules or those active nutraceuticals, nutritions, which can be added to the food materials, which can, can protect them under microwave when we are heating our burgers, and or they can be added to our drinks, and it will give the positive things to our body. So it is important to use bio-based materials. Generally, what we are doing, we are using gelatin, we are using plant-based oleochemicals or the byproducts, for example, keratin from say chicken feather, or we are using oleic acids or many other materials from vegetable plant seeds, which generally we throw away, right? All these are highly active reagents they can be converted into. It can help in, if any material, it has been reported that if their structure is in nano range, the digestion is very high because of that, right? So yeah, so these are the protein molecules which we can extract from any particular material. And but only thing, we cannot just add this protein molecule to the food. We cannot add these lipidic components to our food, right? We cannot, because that will change the texture, taste. We have to convert, we have to formulate them into particular structure that we can use for our applications. So we know that through these materials, only with these materials, proteins, lipidic contents. And I hope you guys also know that the COVID vaccine, which is made up of, it is also a combination of this lipidic system. That is a lipid-based emulsion system, which has been used for delivering that particular mRNA to our body, right? So they are highly important and they have a very bright future, and a lot of research is going on. So these are different nanomaterials, or I will say delivery vehicles, because right now we are, what's the property? So remember, the material is nano, so it is nanomaterial, but depending on the application, depending upon what particular thought process we have, the application, the change, we change the terminology. So right now, I'm not saying it is a nanomaterial, I will say it is a nano delivery vehicle. Why nano delivery vehicle? Because they can help us to deliver particular material, particular drug, particular vitamins, particular minerals from one place to another place, right? So this is what I have synthesized. So I have synthesized layered nanoparticles, which can encapsulate a particular drug or nutraceutical, that is resveratrol. It has anti-cancer activity properties. It is also, it is also considered as a nutraceuticals, which is mostly found in grapes, and it helps. It is a strong antioxidant. We all need antioxidants, right? To look young, to be active, and all that. So we are forming a layered material where there's a layer of the protein molecule. Because it is a protein molecule, it is not toxic to us, right? And it can also bypass the system, and it will be dispersed in water, right? And inside it, which is having the lipidic content and is capturing the drug molecule. So in all these cosmetics, medicines, even cheese, I didn't have the image. If I show the image of cheese, you will see there will be protein structure, as I showed you in the hydrogels, and there will be lipid contents in between. So that's what cheese is actually, if you see it through scientific point of view. So there are various products which are using this particular technique. So what we can do, so this is what actual research is, or I will say the basic research thing which is happening is, by altering the concentration of the lipidic content, how we are mixing it, how we are forming it, the thickness of the layer, thickness of the protein, right? The thickness of the core will change every time. Whenever we do any changes, see, these are the 50 nanometers, these are 320 nanometers, these are 46 nanometers, everything will change. And because of that change, the properties will change. The stability to particular environment will change. The digestive ability will change, right? And all that will be studied, and all that can be used will be processed from lab to industry. And so if it is good, it will go to the industry and it can come to you. So ultimately, so conclusion or take home message is, fabrication of novel hybrid nanostructures to help whole ecosystem. You have to understand that we have to formulate certain structure in nano range, which can be beneficial to us. They can be toxic at certain concentration, but we have to study it. We have to understand at what concentration they are toxic. So we have to avoid that particular concentration and formulate those materials for different applications. We have to figure out what particular application they can be. So then we have to specifically study applications, specific application, because a particular material can be used for many applications, various applications, the same material. Zinc oxide can be used for, say, antibacterial activity. They can be used for antifungal activity. They can be used as a, perovskite structure, electronic properties, solar cell. They can be used in solar cells also. So a particular material can be used for many applications. So you have to verify, or you have to follow a route. You cannot be, like a mixture. That will be very difficult. So you can synthesize the material. You have to be specific in that, and then should follow with the specific application. But because it will have different applications, you should always do interdisciplinary research. You should make friends, as I did in biochemistry. So you should make friends in different areas, and you can use those materials. So also these nanomaterials are highly used in these sectors, which I did not discuss in this particular time. In energy sector, we are using them for hydrogen generation. We are using nanostructure for hydrogen storage, because we know that hydrogen is highly flammable. So if we can just fill a cylinder, it will be a bomb. So we are storing hydrogen inside these nanostructures so that they will not burn at a time, so that they will be more stable. They can be transferred from one place to another place. If you know that China has already started production of hydrogen using nanomaterials for, for splitting water and generating hydrogens for energy. Then electronic sector. So most of the Silicon Valley, mostly employing silica oxides or silicon-based materials or different materials. And because of different electronic properties and optical properties, they are, using them as a gate, in electronic properties. In batteries, there are so many limitations for batteries. We know a battery is storing charges, right? There is an electrode, cathode, one anode, but they get corroded and they are polluting the environment. They don't have that big life. And nowadays, our cars are running on batteries. And in future, you can definitely expect that the hydrocarbons, the petroleum oil-based vehicles will go away. It will already, surpassing, and more electronic vehicles are increasing. So people are improving the stability, or I say, battery power, using forming nanostructures within the material, within the battery. They are forming lithium-ion batteries, right? We can use a simple lithium bulk rod, but what they are doing, they are forming nanolithium. They are modifying that particular lithium with different nanomaterials, and based on those research, they are increasing the battery or the storage ability of the material, and things will change. So a lot of research is going on in nanostructure, nanotechnology, and battery areas. Then if we talk about, as I already discussed, that in vaccines, nanomaterials are used a lot in, for example, simple silver-based disinfectants, right? And also in COVID vaccines, I told lipid-based nanostructures have been used. And nowadays, people are fabricating masks through nanotechnology. They are forming nano web within the material, within the fabric, which helps not to so that the material will be breathable. Because if we are putting mask all the way, all the time, what's happening? Our lungs are getting affected. So people are getting smarter. They are forming material which are light. We can take air in. But if we are sneezing, I'm affected, I have infected, and if I'm, breathing out the virus, it will not pass through the cloth, because there are, first of all, there are some nano channels. Secondly, there are some metallic nanoparticles, say may silver, may gold, or say some other active material, which can deactivate these virus molecules, these protein virus molecules, and will protect people. So, after, like, concluding my talk, I will say that nanotechnology is everywhere. You just have to observe, you just have to think about it, that how this particular material at that particular range is being used, right? Just think. And even nature, you can see that everywhere there is nano. You can see the effect of shape, the structural change, how it is changing the chemistry, physics, or biology of that particular material. So these are a few references, some books which you can follow through. And always there is a Google Scholar, right? ResearchGate. You can always follow up. And nowadays, you guys know how to use internet better, so you can always Google it, right? But read the scientific journals to have some scientific idea, not just any Google page. So in this path, I made some good friends, like Dr. Abhijit, and, and it's pretty cool here. So finally, I will thank again all my friends, supervisors, friends, and the organizing committee for allowing me to present the work. Thank you. And if there are any questions, definitely I'm happy to answer.
Thank you very much, sir, for this insightful talk. It was indeed a great learning experience. Now we can begin the questionnaire session for today's workshop. I would like to ask the questions participants have posted in the chat box.
Definitely. Okay.
The first question is from Karishma. Where will nanotechnology take us?
To the moon, definitely. We are going there, yeah, even in Mars. So I will say, even if you say what Elon Musk is doing, right? So definitely there is the application of nanotechnology. We are using certain materials which are lightweight, but we are trying to develop certain structure, as I showed, the spider web, or say honeycomb structure, which are very strong because of the geometry. People are trying to explore it, why that particular geometry is that strong. So nanotechnology is everywhere. We are trying to use that for different development aspects. And yes, because of this technology, we are going to build a number of things.
Next, Ria has asked, what do you feel the repercussions are for extended life through utilization of nanotechnology?
See, this is a philosophical question, to be honest, right? So, because if we are not very sensual, or we are not respectful to each other, we are definitely going to kill each other, or we are going to harm each other. Nanotechnology is definitely helpful in extending the life, but how we use that particular life, that's up to us, right? So this is a technique, or I will say this is an instrument, right? A method through which we can make our life easy, which we are doing every day. But that's all. But it is not teaching us to harm anyone. It is not teaching us to, only get the benefit. So that's all different. But technology is definitely for our own benefit. So we should use it for in a positive direction. We should not take it in a negative direction.
Next question is from Aditi. What are some of the most interesting nanoparticles found in nature, not manufactured in the lab?
This is a very interesting question, right? In nature, if you say chlorophyll, right? We know it's a compound, but the metallic component in it is always in nano range. There are some rivers, right? And they have some antibacterial healing ability, some soil. Generally, if you talk about some ancient times, we used to say, okay, put that particular, okay, it's cut, just put the sand, put the soil. It has healing property. So generally, the sand was not like, it didn't have the healing property. The only thing which it has, at that time, there was no pollution. So first is that it's clean, it will stop the blood flow. And secondly, it had minerals. say iron, some of the say Kurukshetra, right? Different soil colors will always tell you what particular mineral is at high state in it. So mostly they are, you know, in nano range. They may be in nano range, but they are mostly in oxide states. They are present over there. That's a natural state, and they have their own beneficial properties. So they are, you can find iron oxide many places. You can find manganese oxide. You can find zinc oxide. So it depends upon the area where you are looking, but there are so many nanoparticles in the nature. Calcium oxide, right? You can find many places. So it's not like that we cannot find it, but yeah, we have to see it where we are looking at. For example, again, if you see, people used to make pottery, which I showed you one example, right? So if it is for, you know, if it is for the use of, say, royal people, say some king, we cannot use any artificial, we cannot use any normal material for it. So generally what we used to put, not we, means the people used to put gold, or people used to put silver, because they were the expensive metal at that particular time. And the process which they follow, or which they followed at that particular time, led it to form nanoparticles. Actually, that's why they are having different colors. But the only thing is that we didn't have the instruments. But right now we have different instruments like transmission electron microscope, scanning electron microscope, to analyze, to visualize, actually to see the structure, shape, size of those materials. Thank you.
The next question is whether nanoparticles have good effect on apoptosis for all types of cancer cells.
No, not all, right? But a few of the nanoparticles do have this particular effect. However, you have to understand, if it is killing a cancerous cell, maybe cancer cell will be more prone to it. They will be easily killed, but they can also kill the healthy cell. That's why that's why the problem, because many people, talk about like this. We are talking about technology, we're talking about nanotechnology, we are so advanced. Why people are still dying of cancer, right? But because we are still unable to figure it out, how only to target the cancer cell, how only to, segregate that particular area and kill it fast, because cancer is very rapid. It changes. It actually kills a lot people. Same as like COVID, what happened. But in COVID, what happened? It spread a lot. It spread throughout the world. But cancer is doing the same within the body. If anybody is affected, it's spreading very fast. So people are working on it, and I'm hopeful this COVID situation has taken a lot from us, from a lot of people, but it has also given us an idea that if we actually dedicatedly work on some particular topic, we can find the solution pretty fast. So hopefully some researcher will come up to it and they will find a particular solution for this issues also. Yeah.
Thank you, sir. Moving on to the next question. Pranjali has asked, what about the use of nanoparticles for COVID-19 cure? Are they being used for this one also?
Yeah, they are used, right? They are used for different applications in this sector. As I told, that lipid nanostructures or nanomaterials have been used for delivery of mRNA, right? And similarly, these nanoparticles are used in different areas, different industry for disinfection, in hospitals, disinfections of buildings in Italy and Milan. So there are different examples where these materials have been used, or as an anti-cancer or anti-COVID application. You can look into the literature. You will find various examples.
Okay, sir. Thank you for this questionnaire session.
Okay, thank you very much.
Thank you, Kaushal. Dear participants, we'll be shortly beginning the validity session in a minute. A very good morning to all of you. Welcome you all to the valedictory session of 3-day workshop titled Hands-on Training Workshop on Green Synthesis of Nanoparticles and Their Biomedical Applications. We had an overwhelming response from undergraduate students, postgraduate students, PhD scholars, and faculty members across the country. These are some of the colleges and universities from where our participants have been. We also had participants from Sri Lanka. This is the list of University of Delhi colleges who participated in the workshop. The workshop started with the inaugural session presided over by the Professor DBP Sarkar, Senior Professor, Department of Biochemistry, University of Delhi South Campus as Chief Guest on Feb 4. Anal Kancha, who covered various aspects of nanotechnology in his talk titled The Promising Cues of Nanomaterial Synthesis Using Bio-Nanotechnology, a truly sustainable approach. He gave a timeline of nanoparticles and even shared nanoparticle-based products of his lab. We thank you, sir, for joining us today as well. On day 2, Dr. Abhijit Mishra delivered the lecture on green fabrication of nanoparticles whose talk aimed at introduction to nanotechnology, rotoscope, and applications. He explained very well the concept of nanotechnology and the growth mechanism of nanomaterials.
Dr. Usha, you are not audible.
I'm sorry, ma'am. There was a technical glitch. I hope I'm audible now.
Yeah.
Okay, ma'am. I'll start from the day 2 itself. So on
Yes.
day 2, Dr. Abhijit Mishra delivered the lecture on green fabrication of nanoparticles and their biomedical applications. He discussed several ways to physically characterize nanoparticles. He also showed how nanoparticles can be synthesized in an undergraduate laboratory easily. On day 3, today we were joined by Dr. Anujit Ghoshal, whose talk aimed at introduction to nanotechnology, rotoscope, and applications. He explained very well the concept of nanotechnology and the growth mechanism of nanomaterials, how these nanomaterials have got application in diagnosis, treatment, and vaccine. We are thankful to all our speakers. Our participants have been sharing their feedback with us on all these days. These are some of them, and they are quite interested in attending more such workshops in future. I request Dr. Ruchi to please play the video. These are video clips shared by our participants. It's not audible, Dr. Ruchi.
I'm going to share the video separately. Just give me a minute.
Okay.
Is it audible now?
No.
About the workshop I
Yes,
attended
it's audible now.
last 2 days it gives me immense pleasure in speaking few words about the workshop I attended since last 2 days, and one more day is left, that is tomorrow. The workshop was conducted by Shivaji College, Delhi University, on the green synthesis of nanomaterials and its applications. On the first day, we had Dr. Anil Kancha, who shared his rich and vast experience on the green synthesis protocol, keeping in view the concept of sustainability and circular economy. He emphasized the fact that yes, nanomaterials can be synthesized from any biological source, and this could be really helpful in the near future. On the second day, we had Dr. Abhijit Mishra, and he spoke about the application aspect. And as I can understand that in the last 2 days, there were close to 120 participants who have gained a lot, and it has generated huge curiosity. And I'm really hopeful that these kind of workshops should be organized on a regular basis, which will benefit the participants, the faculty, and the students equally. Thank you very much.
I, Dr. Rangnath Ravi, Assistant Professor, Department of Chemistry, would like to congratulate entire organizing team for a wonderful hands-on workshop on green synthesis of metal nanoparticles and their biomedical application. It was a splendid event, both in terms of speakers, intellectual quality, and information. The workshop was smooth and efficient throughout. Whole team can be proud of their hardworking colleagues and volunteer contribution. Thank you.
I'm privileged to participate in this workshop, which is proving to be very fruitful. Hope Shivaji College team will continue to organize such academic events for the benefit of students and scholars as well. Thanks.
I'm Aditi Ratan, student of BSc Honours Biochemistry, 6th semester. Our department organized a hands-on training workshop on green synthesis of nanoparticles and their biomedical applications, focusing on the promising cues of nanomaterial synthesis using bio-nanotechnology and green fabrication of nanoparticles and their biomedical applications in the first 2 days of the workshop. This workshop helped boost the scientific temperament of students and to enable them to think out of the box. I thank all our keynote speakers for enhancing our knowledge about the nanotechnology. Thank you.
Thanks for giving me this opportunity. I am Dr. Prabharya from Deshbandhu College. It has been really nice experience to attend this hands-on workshop. And the speakers for 2 days we have listened, they were really nice. They explained the concepts really well. And it was amazing to know that the things which we are using in our kitchen, they can be used for preparation of nanomaterial. And you also learned the biomedical applications of them. And also it is really nice experience to see that how the nanoparticles are actually prepared in the laboratory, how you can see visualize the color changes in the nanoparticles. Thanks for organizing this type of workshop. It has been really learning experience for us faculty also, and I'm sure that it would be benefiting to students also. Thank you. All the best.
Thank you, Dr. Ruchi. Now I request some of the participants to share their experience by unmuting their mic.
Hello.
Yes, sir.
Ma'am, can I share it?
Yes, please continue.
Ma'am, my name is Sameer Rai. I'm from Central University of Gujarat. I'm a student of MSc Nanotechnology over here. Ma'am, this workshop has been a very good workshop. I have been in several workshops till now, and this is one of the best because over here, apart from being a part of this workshop, we have gained very much knowledge about the synthesis of nanomaterials, but moreover, In this workshop, I gained the knowledge about the biomedical applications, which is one of the most important and very crucial part of nanotechnology. So thank you for your entire team, ma'am.
Thank you. Any other participant?
Good morning, everyone. I am Vinayak Joshi, currently pursuing MSc Biochemistry from University of Delhi South Campus. Passed out from this very department, Shivaji Department of Biochemistry, Shivaji College, University of Delhi. Firstly, I would like to thank everyone from the department for organizing such interesting and informative session, the 3-day session. All these sessions were pretty informative and interesting, and I would say more of fascinating, because we all hear about like the nanoparticles somewhere or sometime, and I don't know about others, but as a student who is not from this field, whenever I think about nanoparticles, I think of extremely sophisticated labs and equipments, and think of it more of a chemist thing or a physicist thing. But this workshop made me realize that all these are pretty accessible to us from biological sciences as well. Now, the first day session by Jha sir and the second day session by Abhijit Mishra sir made me realize that it's pretty accessible for all of us from biological sciences. And especially yesterday's session by Mishra sir, where he showed the synthesis from our own college's lab. It was pretty interesting to see. And finally, today's session by Ghoshal sir gave a deep insight into the chemistry and varied applications of nanotechnology in these different fields, many of which I feel like we come across on the daily basis, but we never think of it in that way. Thinking of it in like it's actually nanotechnology going on there. And I'd like to thank all the speakers of the 3 days for making these presentations very palatable and like simple for, especially for us students, because as students from these biological sciences, many times this touch from these chemistry and the basic sciences weakens. However, like everything circles back to basic sciences again and again. Now, once again, thank you to all the teachers, all the organizing committees, all my like juniors from the Department of Shivaji College for organizing this session. And as always, looking forward to attending more such informative sessions. Thank you.
Thank you, Vinayak, for your kind words. I request other participants also to please share your feedback.
Good morning, everyone. My name is Merlin Matthew. First of all, I would like to thank the Department of Biochemistry, Shivaji College, for organizing this 3-day workshop on green synthesis of nanoparticles and their biomedical applications. During this 3-day session, I got to learn a lot of new things, like what nanoparticles are, about nanoscience, the various techniques which are used for characterization of nanoparticles, the biosynthesis, the applications, and their scope. I am sure that this workshop would have been beneficial for everyone who has attended it, and I would like to attend more such events in the future also. Thank you.
Thank you, Marlin.
Good morning. This is Dr. Dilshad Begum from JBAS College in the Department of Zoology, Chennai. I would like to congratulate first the Department of Biochemistry and the organizing secretary and the organizing members, those who have selected such a wonderful topic, which is the need of the hour, where we thought like from the biological background, I thought nanotechnology is only meant for the physics or some other departments or for the engineering students, but it was so, wonderfully the speakers have presented. The presentation was so lucid, and I would like to thank all the speakers that they have explained in such a way so easily in our simple laboratories also we can able to synthesize the nanoparticles. Only thing we need to practice it and put it into our efforts, that we can also do a simple work in the great works in a simple labs. So that was the message I just want to take it particularly to my heart, and I congratulate once again the department members who have organized such a wonderful workshops. Thanks for the opportunity you have given to all of us, and keep posting such invitations to us. Hope we will be joining in each and every program as you have been sending the invitation. Thank you so much.
Thank you so much, ma'am, for your encouraging words. So with this, I think participants, please note that you will receive your certificate on your email in a week time if you have attended all the sessions and filled all the feedback forms. So before we move ahead, I request everyone, please switch on the video for a virtual group photo. Thank you. Thank you all. Now I invite Dr. Renu Bavetra, convener, Star College Scheme, to kindly deliver a vote of thanks. Over to you, ma'am.
Thank you so much, Dr. Usha. I, on behalf of entire organizing team, feel privileged to deliver a formal vote of thanks of the 3-day hands-on training workshop on green synthesis of nanoparticles and their biomedical applications, organized by Department of Biochemistry, Shivaji College, under the aegis of DBT Star College Scheme. To begin with, I express my deep gratitude to Professor D.P. Sarkar, who had kindly agreed to be a chief guest of the inaugural function in such a short notice. His constant support always motivates us to organize more such kind of events for the benefits of students and faculty. My heartfelt thanks to our resource persons, Dr. Anil Kancha, Dr. Anujit Khoshal, and Dr. Abhijit Mishra, to share their knowledge with us and answer all the questions of the participants with patience. I wish to express my sincere thanks to our principal, sir, Professor Shiv Kumar Sehdev, for his constant encouragement in all our academic endeavor, and our Star College Scheme coordinator, Professor Darshan Malik, for her enormous cooperation in organizing this workshop. I would also like to thank our event organizers, coordinators, student volunteers, and our support staff for complete preparation of this workshop, and our participants for making this workshop a grand success. Their positive feedback motivate us to organize more such kind of workshop, and we will definitely try to do so in future. And as someone asked, we will definitely try to post and circulate it to as much as participants as possible. Last but not the least, we gratefully acknowledge the financial assistance of Star College Scheme of Department of Biotechnology, Ministry of Science and Technology, Government of India. Once again, I thank one and all who have joined and maybe directly or indirectly associated with this workshop. Thank you so much. Over to you, Dr. Usha.
Thank you, ma'am. So with this, we conclude this workshop. Thank you so much for joining us. Thank you all the participants, and thanks to all the speakers.
Have a nice Sunday. Bye-bye. Thank you all. And thank you, Dr. Anujit. Maybe very late night for you.
Yeah,
thank you so
late,
much.
but yeah, thank you. Thank you, everyone.
Okay.
Have a good Sunday.